In this next video, let's take a look at page tables in action. All the way to the left over here, we have the processor that is interested in accessing a memory location. In the middle of the slide, we have a page table that is used for mapping or translation of page numbers to a frame number or a disk address. All the way to the right, we have a dynamic RAM and a secondary hard disk. We have a 32-bit virtual address which includes a field for page number and a page offset, and we also have a fewer number of bits in the physical address where it has the field for frame number and the page offset. In the page table, we have the page number, that's the index. We have a bit for valid. One means it gives you the mapping between the page number and the frame number. Otherwise, if it's a 0, it means that we could have the information on the disk and you probably would need to access that. So let's see how all of this works. So if we assume that the processor is right now executing a program, and an active program is called a process. So if it looks up a 32-bit address, in this case a virtual address, we know those 32 bits, those are those two fields. Next, we need to find the mapping or the translation for the page number. So we look at the page table, which by the way is in the physical memory, which means that we already have one memory access, which might not be a very good thing in terms of memory access times. We will look at that in the next video. Now in this case, we got lucky. We have the valid bit set to 1, which means that the page table readily gives us the frame number, which will fill the frame bits in the physical address. The offset, page offset, does not need any translation, so that's copied over to the physical address readily. And now we have the 30-bit or some bits that are less than 30, those number of bits readily available in the physical address. And by using that, we can access any one of the M frames and bring that information to the CPU. Now this was good because we had the valid bit set to 1 and we had the frame information. What if the valid bit is 0 and instead of looking at the physical memory, we actually need to access the disk or the secondary storage, which increases our access times tremendously. If the valid bit is 0 and we are trying to access that corresponding page, that means that we have a page fault. Page fault rate is the fraction of page table accesses that result in the disk access. Now we would probably need to access that page that we are missing in the secondary storage, which means that I need to replace a page from the physical memory. So I'll need, if it is full, I will need to replace the page from the memory, put that back into the disk, or save it to the swap space and bring in the new or the updated information into the main memory. Now we need this swap space so that when we remove or relocate that frame, we have a place to have a copy. In fact, that swap space has a copy of all the pages, whether those pages are present in the RAM or not. So for example, in the case of this valid bit being 0, it is not going to be present in the physical RAM, and that page was on the hard disk. Alright, now let's take a look at an example here where a particular program has several pages that is trying to access, but the physical memory only has a few pages. So All the way to the left we have a virtual space of a particular program. In the middle we have the corresponding programs page table. On the right we have physical memory and the disk. DA stands for disk area, and there are 8 pages in the virtual space. Those are marked A through H. All those 8 pages have a corresponding entry in the page table. Some of the bits are valid, they are set, and some of them are off or 0. So let's try to see what happens when we try to access page 0, for example. So page 0, which is marked by A, when we try to look up the page table for the translation, it says page 0 has a valid bit of 1, and the information that we are trying to access is in frame 1. And that frame 1 corresponds to the same marking as A. Now, it works the same way for B, A, E, and F. So those are frames 0, 1, 2, and 3, which is frame 1, 0, 2, and 3. So those 4 entries in the page table will have a valid bit of 1. They are also stored in the hard disk at those 4 disk area locations. So in this case it is 1, 2, and 5, and 6. So that would be 1, 2, 5, and 6. So A, B, and E, and F. Those are my 4 entries in the physical memory. And as you can see, some of the information that is only on the hard disk is not present in the physical memory. So what happens if we try to access, say for example, page 3? So when you try to access page 3, we are going to need to look at the page table, and page table says valid bit is 0, and we do have a disk address which says disk address is 4, disk area 4. Disk area 4 says is the same marking D. So we will need to pick a particular frame that needs to be replaced, bring in D from here to the physical memory, and then update the page table. And the operating system is responsible to do all of that. Now there is one more thing that is happening in this example. We have 8 pages, however page 6 and 7, the marked G and H, those 2 pages are not in the disk, which means that if the CPU tries to access page 6 and 7, and as you can see it does not have any frame number and it does not have any disk address, it is going to give you an invalid reference and it's going to abort that program. Now let's see what happens and how does the operating system handle a page fault. Page fault is when we try to look up the page table and we have the valid bit set to 0, and we need to look at the information onto the secondary disk, a hard disk. So how are we going to handle it? So let's suppose we are trying to execute this particular instruction, which is a load word instruction, and we need to load a word based on an address into register number 20. It doesn't really matter what the exact details of the instruction are. We're just trying to simply load a word, for example. So whatever word we need to load in, we need to load a word into a register. So we need to access the memory for that, and that corresponding page number is going to be have to look at in the page table, and it turns out that is absent in. So the valid bit is 0 for that corresponding page number, which means that the word is not in the dynamic RAM. But we do have the disk address over here, and the page fault essentially initiates a trap addressing error to the operating system. In response, the operating system is going to initiate a disk I/O. The result of which is going to be to find an empty frame in the physical memory and put that corresponding page into the physical memory. And once we do that, we are going to have to update the page table we'll first have to make the valid bit into 1, which means that we have the word that we are looking for it to execute that instruction in the dynamic RAM, and we are going to restart the instruction. In the meanwhile, we will have to stall. So that's how we are going to handle a page fault. Now let's see how we can calculate performance or try to associate times to all of this. So suppose we are trying to do a memory access, and say we have a cache that we are trying to access first, and then we go to the memory, and if we don't find things in the memory, then we go to the hard disk. So at the beginning, we could have a hit in the cache, or we could miss the cache, depending on the hit rate and the miss rate. Miss rate is essentially 1 minus the hit rate. But we have C, which is the cache access time. That's going to be the time that we take to access the cache memory. Now if we do have a cache miss some of the time, some fraction of the time, then two things might happen after a cache miss. We could find the required word in the memory, or it's not present in the memory and we have a page fault. P, small p, is the page fault rate. So 1 minus p is going to be the rate at which we will find things in the memory that we did not find in the cache. So for those fraction of the times, we are going to have two access times that are going to add up. C, because we already spent time trying to access the word in the cache, and M, because that's going to be our memory access time. And if we don't have the word in the memory, then we try to look at it in that's a page fault, and we are going to have to spend a lot of time, which is going to dominate all the rest of the times, because that's going to be our disk access time. So that's going to be very huge in comparison to all the other times on this chart. Now, how do the real world page tables look like, and what are some entries in those page tables? We have already talked about having a one page table per each program, and it's a good idea so that we do not have any sort of collision between pages from different programs, and if every program is secure that way. A typical page table will have all these fields, and we are going to add more to it later on. The valid bit, we have seen this several times, it functions the same as it did in the cache memory. When valid bit is 1, that means that the page table has information about a frame. If it is 0, that means that we'll have a it could be on the disk. Dirty bit, it means that if it is 1, that suggests that the page has been modified, just as in the previous example we discussed. And it is important to know this because if we change the physical memory and we are trying to replace that particular page, we will need to monitor that because we are going to have to update that in the hard drive as well. Reference or use field, that is used to estimate the least recently used pages, one of the page replacement techniques. Protection bits, for example, read protection for that particular page, write protection, read and write protection. This is particularly important when we have multiple processes that share the pages. Frame number, that gives us the physical page number, or another alternate could be, if it's not on the physical memory, then it's on the disk, and one of the fields should give you the location on the disk. Alright, let's stop over here for this video and then pick it up with the translation look aside buffer in the next video.